lecture 21, yes. Page number?
Yeah, so in this lecture, we observe the structure of the operators in the TFIM, and we see that they form an algebra.
Yes, correct.
Yeah, then we construct a dual lattice,
Yeah,
and then we see that there also we have the same algebra.
correct.
Then we do a mapping.
Yes.
Yeah. So when that mapping is done, uh, 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 then we see that the results that we were getting earlier when we were
Hmm.
changing H and J, the rows, then it were getting reversed. So through this we understand it, but I did not get your uh, uh, the slide number 20, slide number 12.
Ah,
So,
12, yes. Ah,
so some thoughts and opportunities. So this
ah,
part I did not get.
okay. All right. So let's just go through this. So look at the first point. Okay.
Yeah,
So when h is equal to 0, uh,
yeah,
then we believe that the ground state of the transverse field Ising model is twofold degenerate. So it is spanned by all up and all down states. So do you agree
yeah,
with this or not?
yes,
But if you look at the ground state of the dual model,
yeah,
that will be unique.
yes,
But this can't be right.
uh, yeah,
This cannot be right because how
yes,
so if you take duality very seriously, then how can a doubly degenerate ground state map to a singly degenerate ground state?
yeah. There
You
is,
see the problem, right?
yes, yes,
Okay,
that's the problem.
right. So now it turns out that the duality is not exact in the full Hilbert space, right? So if you look at this mi operators, and
Yeah,
let's say that you use periodic boundary conditions, then
yeah,
if you take the product of all the mi operators, that will become identity.
okay,
That means if you now write the mi operators in the dual language,
yeah,
the product of x tilde I is identity. Correct?
yeah,
But this means, so why am I saying x tilde I has to be identity? Because this is a map of operator algebras. So if it is a map of operator algebras, identity in one space will map to identity in the other space. Otherwise, it will not be a map of the algebras.
yeah,
Ah. So that's why I'm insisting that product I tilde, m tilde, I tilde this is the third point. Correct. Sorry, the
yeah,
second point, which x tilde, I tilde equal to identity. But you
yeah,
know that x tilde, I tilde cannot be identity, right? X tilde, I tilde is the generator of the flip transformation in the dual language.
yes,
So what this means is that you have to work in the subspace of the Hilbert space where product x tilde, I tilde acts like identity.
okay,
Okay, so and now you see, if you now look at the same argument from the dual side, that will force, that's the point number 3, that will force that product I xi is identity. Okay,
okay,
so now you now use this idea and ask, what is the space that is spanned by up and, that is, now go back to the point number 1, up and down spins, sorry, the fully polarized up state and fully polarized down state. What subspace of the space spanned by those two will be flip, will transform like identity under flip? Understood? Hello?
okay. So,
So that is the state 1 by square root 2 all up
yeah,
plus all down, right?
yes,
And now this
yes,
state is unique. There is no other state which will transform like identity.
okay,
And that is the state that maps to this right arrow tilde in point number 1.
Okay.
So the
Yes.
statement is the following. The statement is that duality is not true map of the Hilbert spaces. The duality will map the operator algebra only as in a subspace of the Hilbert space of both models.
Okay.
Okay. Now, so now this is extremely powerful in the following sense. Now imagine that you are at the duality point where H is equal to J.
Yes. Okay.
Right? Now you see the duality will bring the Hamiltonian back to itself.
Yes.
The question now is duality a symmetry? Correct. And it turns out that it can't be a symmetry because the duality is not operative on the full Hilbert space.
Yeah.
This is why such symmetries are called non-invertible symmetries. So
Why
you
the
can
word?
imagine this to be a symmetry provided you allow it to be non-invertible. What that means is, if you take any state in a Hilbert space and map it by a symmetry operation, there will be some states for which you can't find the inverses. You
Okay.
understand? Because, so for example, if you take some state which is all up minus all down by root 2, if you use the symmetry map, that will map to some random thing which you cannot find the inverse of, because the symmetry operation of going from JH to HJ, which will become a true symmetry operation at when H is equal to J, will operate only in a subspace of the full Hilbert space of the system, not on the full space.
Okay.
Because it operates only on the subspace of the system, it's not invertible.
Okay.
You understand what I'm saying? So see, I'm saying that there is a map between, see, there is one Hilbert space with some set of states.
Yeah.
Okay, let's say the basis of that, let's say the dimension of that Hilbert space is 10.
Yeah.
Okay. Now, I have another Hilbert space which is also 10.
Yeah.
Now I'm defining a map in which certain operator algebra is exactly mapped on dimension 5 of one Hilbert space to dimension 5 of the other Hilbert space.
Okay.
But it's not true that map is not true in the full Hilbert space. It's only true in a subspace which is 5-dimensional.
Okay. Yes.
So now if you restrict the whole thing to 5-dimensional subspace on both sides, then when H is equal to J, like in this case, the Hamiltonian will map back to itself. You see, the form of the Hamiltonian will not change because H is equal to J.
Yes.
No, are you following what I'm saying? See,
Yeah.
so you look at the dual Hamiltonian. I'll just show you on. Let's say you look at page 13. Page 10.
Yes.
So we started off, page 10 has the blue Hamiltonian, which is our original Hamiltonian, and the
Yeah.
orange Hamiltonian, which is dual Hamiltonian.
Yeah.
Correct. Now, if H is equal to J, what is the difference between the old Hamiltonian and the new Hamiltonian? Nothing, right? Because the
Yeah.
operator, the coefficient multiplying X, the transverse field term
Yes.
is J, and the coefficient multiplying the ZZ term is also J.
Yeah.
So it looks exactly like the previous Hamiltonian.
Yes. Yes.
So when H is equal to J, so when do we say some operation is a symmetry? When it brings the Hamiltonian back to itself, right? That's when we call
Yeah.
it symmetry.
Yes.
But you see, now the symmetry can be implemented only in a subspace. You cannot implement it on
Okay.
the full
Yeah.
space.
Yes.
So this kind of symmetry, which is valid only in a subspace, is called non-invertible symmetry. Non-invertible means that the transformation doesn't act unique. So that means that if you give me some arbitrary vector, I give
Yeah.
you the image of that vector, you can't tell me which vector it came from. Many different things will go to the same vector. So it's not invertible.
Okay.
Yeah. So now people have understood that in non-invertible symmetries are very important things in physics. And so if you look at this paper, this is some 2025 paper, you know, the Shao, etc. et al. So that will give you some idea about non-invertible symmetries.
Okay.
Yeah. Okay. Yeah, I'll just check. Okay, so I just want to address there are a couple of questions from the uh, the Google document. Let me address them. Uh, is constructing dual of the transverse field Ising model, the states of dual lattice were taken to be midpoints of the links of the original lattice. Is this just a schematic to emphasize the dual Hilbert space is different from original one? Wouldn't any set of two n objects? Yes, that is correct. It is indeed correct that it is a schematic to show that it is different from the original one. Indeed, any set of two n objects satisfying algebra is independent of site position. That is correct. That is a correct statement. Okay, second question. In quantum mechanics, operators of the dual model satisfy the same algebra of the operators of the original model. Are there similar constraints on duals of classical models? Yeah, but is the dual is the same symmetries as the original model? Okay, so let me address the classical question first. So in classical mechanics, there is no direct meaning for algebra of operators, right? So there is no direct way of sort of mapping some algebra of operators. So in typically classical duality, the way you try to get the duality, like we did in the transverse field Ising model, is to try and define some other set of variables which will give you essentially the same partition function as our original model, except maybe some analytical functions, right? So if the free energy has some extra analytical function, we don't worry about it. So that is how your duality is constructed. So in the sense, mapping operator algebras is much nicer, has a much nicer mathematical structure, and therefore the quantum dualities are definitely in a nicer mathematical, it's mathematically more aesthetic in that sense. Second question is, a related question is that the dual model must have the same symmetries as the original model? Okay, I will not answer this question in great detail because there are a couple of homework problems and the homework problems that are coming your way for you to think about. So maybe what I will do is I will answer this question 2 weeks from now, but I'll just drop a brief hint. The answer is no, they don't need to have the same symmetries, but there should be something common between the original model and the dual model. So I think people should just think a little bit more about this, and after a couple of weeks we can take this point again and discuss this. Okay, so this question is from Mrinal. Okay, next question is from Senthil Kumar. Okay, so there is notes PPT. I don't understand. There is no question written per se. Not entirely sure what the question is. So, okay. All right. So I'll go back to the online session. Okay. So if there are more questions, we can take them.
So, could you
Yes.
tell something about anti-periodic boundary conditions? I mean,
What do you mean by anti-periodic boundary conditions? That's what you're asking.
No, I mean,
Uh,
we use periodic
okay.
boundary.
Okay, all right. So I have to use the blackboard for this. So if you don't mind, I'll just share my screen. Um, so let me explain to you what do you mean by anti-periodic boundary conditions. Oh, sharing is not turned on. So maybe I'll just ask the moderator. Okay, now I'm able to share. Okay, all right. Okay, all right. So let us try to understand what do you mean by anti-periodic boundary conditions. Okay, so why is this blue thing coming here? Okay, I'm not sure, but let's proceed. Sorry, I'm struggling with this. Okay. All right. Very good. Okay. So okay. All right. So now imagine that I am sitting on some kind of lattice. Okay. So imagine that I have some lattice. I hope you can see my screen. Hello?
Yes, I can see the screen.
Yeah. So this is a lattice. Okay. So what I'm going to do is I'm going to define some function. Let me call this lattice site as I, and I'm going to define a function psi I. Okay, and I have periodic boundary conditions. I have 0 and I go all the way to n minus 1, and this will be the nth site, but I identify the nth site with 0. You're okay with this? That's the periodic boundary condition. That's like connecting.
Yes.
That's like connecting this to this, right? So that's okay.
Yeah.
Now, what we can do is we can say that psi n is equal to psi 0. This is what is conventionally called as periodic boundary conditions, right? But
Yeah.
I will do this slightly generally so that you will be able to see this more generally. In fact, if you read some papers, you will see this also happening. But what is called as a general twisted boundary condition or a general boundary condition is you say this is true. Okay, so when theta is equal to pi, that is called anti-period. So theta equal to 0 is called periodic boundary conditions, right? Theta is equal to pi is called anti-periodic boundary conditions. Is that okay? Do you understand the definition, right?
Yes. Yes.
So if it is anti-periodic, that will tell you that psi n is equal to minus psi 0. Okay, all right.
Yeah.
Now, what does this mean? Let's try to understand what it means. So now, when I have psi I, there is a very nice way to write psi I in terms of its Fourier transform, right? So psi I can be written as 1 by square root n sum over all the k's e to the I k xi, right? So xi is the coordinate, right? So this is xi equal to capital I times a. A is this spacing. Okay, right? Times psi k, right? And k will take values. So we'll decide what values of it will take. Okay. So now how do we decide the values of this? So now you see, you take this form that is there. So I'll take this form here. Edit, tools, select rectangle. I will just cut this out. Right, and control C, I'll just paste it here, control, okay, all right, okay, so I'm going to take this and I'm going to use these boundary conditions, okay. So you see, this is the Fourier transform. Now I'm going to use this boundary condition and it will tell me what are the allowed values of k. You're following me, right?
Yes.
So it's going to tell me so what I'm going to do, I'm going to take this formula and stick this thing in. So what that will tell me is that psi n is equal to 1 by square root n sum k e to the power I k n a. Right here, I'm putting xi is equal to
Yeah.
n a. Right, psi
Yeah.
k, correct?
Yeah.
Right, is equal to, so that is the left hand side, this is LHS here, and now I'm writing the RHS, right? So that is equal to e to the I theta divided by square root n sum over k e to the I k n a psi k. Sorry, there is no e to the I k n a here. Sorry, I'm making a mistake, right? Because it's x equal to 0. So when I put x equal to 0 here, everything will become 1. You see that, right?
Yeah.
Yeah, so sorry, I just made a mistake here. Okay? So it will be just psi k here. You see, so this is exactly this thing evaluated at at x equal to 0. Okay, now these two equations have to be true for every value of psi k. Whatever value of psi k you choose, this has to be true. Correct, right?
Yes.
Agreed, right? So
Yeah.
that tells you that e to the I k n a must be equal to e to the I theta.
Yeah.
Okay, so now let us start by simple things. Okay, let's choose theta equal to 0. So this is PBC. So when
Yes.
theta equal to 0 and periodic boundary conditions, what will you get? You'll get e to the I k n a must be equal to 1. So that will tell you that k is equal to 2 pi some integer by n a. Right? M is
Yeah.
integer.
Yes.
But since we are on a lattice, this has also to be between minus pi by a and plus pi by a. So this is called the Brillouin zone. So you will get n k points between minus pi by a to plus pi by a, which are of this form.
Yes.
Now let's see what happens when it is, and so this is what happens for periodic boundary conditions. For anti-periodic boundary conditions, you will see that theta will be equal to pi, and this will become minus 1. So this is anti-periodic APBC. So the condition is e to the I k n a is equal to minus 1. So now you see k n a must be an even integer, right? So it will be like 2m plus 1 pi by n a. Understood?
Yeah.
So what the boundary condition will do is, it will change the allowed value of k vectors. You will still get n k vectors. There, if you look at all the k vectors between minus pi by a and plus pi by a, right? You will get n k vectors in both cases. But which k vectors are chosen will be different. That's what periodic or anti-periodic boundary conditions will do for you. In fact, any general boundary conditions also you can solve exactly like this by putting this theta, and you will get some different values of k's. Hello?
Yeah. So, what's the physical? I mean,
Uh, okay. So physical means, okay, I don't know what, how much of quantum mechanics, etc. you have studied, right? So, uh, if you look at quantum problems, this, so what is going on here? See, if you impose this kind of boundary condition, it tells you that if, say, some particle starts here and does some hopping and comes here, it says that it will pick up some extra phase.
okay.
So what this physically will correspond to, this change of boundary condition will correspond to, if you make this thing into a circle by identifying this, right? It is like having a
Yeah.
magnetic field going through this. So this phase can be thought of as the flux, integral of the
Oh, okay.
flux of this magnetic field. Right, and
Okay. Yeah.
yeah, that you might have studied in quantum mechanics, that if you do some gauge transformation, that the wave
Yes.
function will go e to the integral a, right? So that integral a dot dl will be the surface integral of B dot ds by Stokes theorem. So this phase will get related to the flux included in this ring.
Okay.
By the way, I just want to ask you, since the others, since who's online, right? So these PDF files are becoming available to you, right?
Yes, yes.
But the other person seemed to be saying that PPT and notes are not available. So I'm not quite sure what is going on. So you are able to download them, right?
Yeah, through Google Drive.
Okay. Oh, they have given a link to the Google Drive, right?
Yeah, yeah.
Yeah. So that person has to get that link. Yeah. Okay. Okay. Fine. Okay. Go on. Okay. Next question. I'll check whether there are any more questions. Okay, since there are no more questions, I'm going to close the meeting. So thank you
Thank
very
you.
much.